Okay, so let's dive right in. For this scene, we're going to create a few different elements that we're going to kind of layer together. And so let's start with the drips coming off of our roof as the first element. So when creating a few different elements for a scene, it's always good to kind of organize them into separate geometry objects. It makes assigning materials and locating where things are and controlling them a little bit easier. So let's create a geometry object and let's call this drips. Before we dive into drips, let's actually just take a quick look at the ENV. And in here, you can see it's broken out into a few different layers. We got plants, roof, house, extra stuff. So let's dive into drips and let's create an object merge. And let's bring in our roof. And there we go. So something that's also important when you're starting an effect is to kind of evaluate the inputs, being the frame range, your camera, what the camera's doing, as well as the geometry or the models that you're bringing in. So we'll take a look at this roof, and it's pretty standard. We kind of come around here. You can see there is no thickness to these tiles. It's just single-sided face. They're kind of jamming in the tiles here. They're just getting clipped there. So in Houdini, a lot of our effects need to require manifold topology. The models need to have thickness to them. They need to be enclosed. So oftentimes we do need to rebuild assets that we do bring in. The other thing I want to look at is if you middle mouse, we can look and see what attributes are coming in with this model. The one I want to put your attention to is the p-scale. If we look at the geometry spreadsheet over here, we can see the values of the p-scale and they're all 0. So that actually can get you into trouble as this attribute would flow through any nodes that you're creating. And the reason is because p-scale is a reserved attribute in Houdini for setting the radius of a point, and then that also filters into a variety of different nodes. So oftentimes if you put a node down and you've got this p-scale with a value of 0, the node isn't doing what it's supposed to do because it's expecting there to be some kind of positive value on that p-scale. So let's go ahead and just delete that with an attribute delete. And off you go. All right, so it's no longer there. If you want to delete that U attribute, and you can delete these others if you want. It's important to keep UVs though. All right, so now let's just kind of rebuild this geometry that's going to work for us. The end goal, just so you're aware, is we want the drips to be emitting kind of off these end pieces here, these end tiles here. We don't really want it emitting anywhere on the roof. We just kind of want to be pouring off these edges. We don't also really want it to be emitting from the underside here. So with all those things considered, let's rebuild this as just in a really basic way. And that's using a shrink wrap. What this does is this creates a convex hull around our geometry. So basically it looks at all the points of the geometry and figures out where the extremes are and creates this, again, convex hull. Let's create a remesh just to give it a little bit more definition. And let's set the target size, something like 0.5 to get more definition. And then we can create a ray and we'll plug our remesh into our first input and our attribute delete into our second. And then I'm going to hit Shift S to just change my noodles to be curvy. So we're going to ray and change from project rays to minimum distance. So it's really just going to find the nearest surface and just push our points to those. So obviously it doesn't look pretty back here. It really doesn't look pretty all over. But for the sake of what we're doing, again, we want to be emitting from these kind of ends here. And the analysis that we want to perform on this geometry, this is going to suit our needs. There's a variety of different ways of rebuilding geometry with VDBs and all that sort of thing. But for the sake of our example here, this is probably going to work. All right. But as I just said, VDBs. So one thing I want to do is use a node called VDB potential flow. And let's just drop that down. We're not going to connect it yet. So we have to do something before. But what this node does is you give it an incoming vector, okay, this background velocity value here, and it's going to then analyze the VDB you feed in and look at how the air would flow around that piece of geometry. So this is really useful for like a wind tunnel sort of vectors or velocities. So in order to use this node though, we first need to create a VDB. So let's create a VDB from polygons. And let's just go ahead and plug that in here. And we can turn this resolution down to something like 0.2. And then we'll plug this in. Give it a second. And okay, visually it looks no different. If I middle mouse, so we can see our original VDB created a surface field, which basically stores it creates what's called an SDF, and that stores in each voxel of this surface field the distance from the surface. So voxels that live outside the model are positive values, is a positive distance. Any voxel inside the volume is a negative number. And then obviously at the surface is 0 or very close to 0. All right, so VDB potential flow, if we middle mouse, we can see we have surface, and then we've got this new field now, flowvel, and you can see it's a vector 3. So that means they're storing 3 values in this field, an x, a y, and a z. And it's all relative to this background velocity. So let's kind of imagine this air were rain. Okay, so rain falls down. So let's do -1 there. And again, not much changes. So in order to visualize this a little bit better, let's create a volume slice. Volume slice. This is always a good way to kind of really check out what velocity fields are doing. Now, okay, there's colors there, but remember, we've got 2 fields, so it's probably doing it for both fields. So let's go ahead and just get rid of our surface field because we don't really need that. All right, so we should just have our flow velocity. Yep. All right, so we now have colors representing the R, G, and B, which is fine. That again doesn't really tell us that much. So let's now append a volume trail. Because this is a velocity field, it's oftentimes useful to look at things using a vector, or in other words, lines. Okay, so we plug our volume velocity or our velocity volumes in the second input, and the points which we want to create trails from. So basically, it's going to analyze each point, and that point is going to sample the voxel, the field at that location, and then it's going to create a line or a trail. And there we go. All right, so if we were to now manipulate our offset, because remember, we're just looking at a slice of this field. We get towards the end, you can see, okay, this is the end of our roof. So if we were to just take a look at this guy here, you can look at and see what the velocity trails are doing. They're all flowing down this way, and then they curve around here. The other nice thing about this is we can see where this color is getting more intense. I think it's using an infrared visualization. You can change it to whatever you want. But you can see this is also giving us the magnitude or the length of that vector. So you can see these higher curvature areas have more intensity. So we can use this information now to figure out, okay, where do we want to emit our geometry. So because this is really intense on the edges, I think that's going to be useful for us to determine and isolate the regions where we want to emit our rain from. All right, so let's go back to our original model up here, and we want to apply that information we got from that potential flow. So this, remember, is just for our visualization, so let's move that over. Let's create an attribute wrangle. And what I want to do is similar to what this volume trail does, where it samples each point of the volume slice and applies that value. I want to do the same with our geometry here. I want each one of these points to sample this flow-vel vector field, and we can then map the intensity of that onto our roof. So let's plug it in there. So right now, this potential flow is outputting a vector field, but our visualization is outputting just a color or an intensity. I mean, yes, this is different colors, so it's a vector, but if we look at grayscale, kind of the same deal. So what I want to do is I want to actually map the magnitude or the length of this velocity field onto our roof. So let's create a VDB analysis. And what it's going to do is take this incoming flow-vel. It's going to analyze it using one of these methods. And you've got these helpful indicators here of the field it's expecting and then what it's going to return. The one we want is length. So it's going to take a vector field and output a scalar field. And if we look now, we can see our flow-vel is now a float. And that's fine. All right, so in our wrangle, now that we have our float field that's storing our length, we want to sample it. So we can use a function called volume sample. And the volume sample function, I just type it, and then when you put the first parentheses, it does do this pop-up help. You can see the usage here and what it does. It returns a float. You give it the geometry that you want to sample, the primnum or the field you want to sample, and then the position which you're sampling from, meaning each point, in this case, it'll be each point of our roof. Well, first we need to create a float because that's what it returns. Let's just type VS for volume sample. It's really arbitrary. Okay, we want to sample the first input or the second input. Sorry, 0 is the first, 1 is the second. Now it's asking that primnum, which is going to be 0, and then the position at which we want to sample the vector field from. So it's going to be each and every point. So at P. And let's just go ahead just to see what's going on at CDVS. CD is our color attribute, and it's a reserved color attribute. So, and look, there we go. All right, not bad. If I go into wireframe, you can see a little bit better. Now we still have things kind of showing up on the rooftop as well as the underside, which is we can kind of now refit these values to try and filter out some of these areas. So let's create a new float for a parameter and call it min, and type ch min, and then let's create a max ch max. And now we can fit our volume sample between our min and max. And then what do we want our new range to be? And we'll just say 0 and 1. So we're basically creating some thresholds, and wherever the max value is going to be, we'll return 1. Wherever the min is going to be 0. And then it's just going to linear interpolate in between those values. If you wanted to, put some different smooth curve or Bezier, things like that, you would need to then funnel it into a ramp. But for the sake of what we're doing, we're fine. Okay, so everything goes white, and that's just because our min and max are 0. If I put this back to 1, kind of turn that up, turn this down, you get more intense areas. Start crushing those lower values. All right, but as we can see, don't know if we're really going to resolve all of that. So I don't know if we're going to be able to filter all of this out. So let's kind of take a look and think about what other properties could we analyze with our roof. And oftentimes in effects, this is what we really have to kind of sit and look at it and find similarities and differences and things like that to kind of figure out how we can isolate stuff procedurally. All right. Well, the one thing I do want to point out is when we look at the faces and the directions they're pointing of where we want to emit. So most of these faces are kind of at a perpendicular to Y, right? They're not pointing down really. They're not pointing up. All these ones that we want to filter out are largely biased pointing up, or they're pointing down. They're on the underside here. And obviously rain wouldn't be kind of collecting and pouring off on the undersides here. I think it's fairly safe to say that most of these faces are pointing outward. So I think in the next video, we'll take a look at something called the dot product, and we can use that to now filter out our things further.